right, it's Wednesday already. Seems like yesterday was just Tuesday. We didn't have school on Monday because of the eclipse. But anyway, today is Wednesday. No book talk this week, but we'll have our next book talk about Mary Roach's Stiff next Wednesday. I put the latest chapter in your classroom for you. Today, we're going to talk about a couple of things as we march on towards the Regents exam, which now is like 9 weeks away. Right, it's on Friday, June 14th, 2024, right, high noon. That's our day of reckoning. So I'm looking forward to that day. And then I retire a few weeks after that, so that's even better. It's an exciting time of year. So let's do today's Bellringer, and then, we'll talk about a few things in class.
All right. Hey now. Mr. Kovacs class. It's Mr. Kovacs class. You might learn a ton. It's Mr. Kovacs class.
It's interesting too.
It's Mr. Kovacs class. And he's super cool. It's Mr. Kovacs class.
Let's talk about stem cells. Stem cells. Stem cells are what we call cells that haven't decided what kind of tissue they're going to become, right? Stem cells are cells that will become some other type of tissue. Now we've learned that every cell in the body has the same genetic instructions, right? But what happens is called differentiation. Some point in this cell's life, it stops reading some instructions and starts reading other instructions, and it becomes intestinal cells. This cell would stop reading the intestinal cell instructions and start reading other instructions to become liver cells, and so forth and so on, right? We call these cells that have the ability to become any other cell in the body, we call stem cells, or sometimes we call them pluripotent cells. We're gonna be looking a lot coming up at embryos, right? The way embryos develop is, right after egg is fertilized, we call it the zygote, right? And then the cell goes through mitosis. And it splits once, it splits twice, and splits. We call it a morula when it's just an undifferentiated ball of cells. Oops. And then when it finally sticks to the uterus, we call that ball of cells a blastocyst, right? And then right at the blastocyst stage, this bundle of cells hasn't decided what it's going to become yet. Once they decide what they're going to become, we now change the name of that to an embryo. Embryo. So it goes zygote, morula, blastocyst, embryo. Zygote, morula, blastocyst, embryo. And when the cells are in the blastocyst or morula stage, they are stem cells. They can become, or even in the zygote stage, they can become any kind of tissue, any one of these cells. Right here it's again, zygote. Right? Then we have what's called a morula, right? A bunch of cells, right, that are all ready to become any cell in the body. What's cool is we've learned that you can take those cells and split them up, right? So you can take one embryo, one morula, and split up all the individual cells, and if you let them go, they will develop into new morulas and new blastocysts and new embryos, which is cool. So that's another way we can clone an organism. We can clone it before it even is born by taking apart its morula into separate cells, separating those cells and letting them develop into new morulas, blastocysts, and embryos. That's pretty cool. This is what happens to identical twins in the womb, right? Mom's morula splits into two blastulas, and they develop as two individuals, right? They're clones of each other. We call them identical twins if they're born at the same time, right? Usually that happens in people. When that happens, that's an accidental thing. It's not, it's something that happens during development of the embryo, but you can cause it to happen on purpose and purposely get twins, right? You can do that. Now, what's really cool in terms of genes and things like that is when you develop into a fetus, right? So fetus is now past an embryonic stage. In a fetus, you have all of your parts. They're in the right places. The cells have all differentiated. They just need to grow bigger. And in our species anyway, and most other mammals, we do this inside mom in her uterus, and then make an organ called the placenta. And the placenta's job is to smush up against the uterus and provide a place for materials to diffuse from mother's blood into baby's blood. Diffusion. The placenta is the baby's own cells, right? The placenta is the baby's own cells. And when the baby is born, mom gives birth to the baby as well as her placenta. Right? What we found is that the placenta is a good source of stem cells, these pluripotent cells, right? So someday they'll be asking you, if you have children, when you give birth to your child, do you want to save your placenta? And you would go, why would I want to save the placenta? Well, that's because you'd want to save those cells, which you could then tell later on to become any other cell, right, that your child might need. Right? Maybe your child will need some kind of lung transplant in the future. Then you can build new lung tissue, right? And the cool part about this, it will be an immunological antigen match to your baby. Right, here's the placenta, and they're drawing blood out of the placenta in this picture to harvest stem cells. Right, so yeah, stem cells are awesome because they can become any cell in the body, right? They can become whatever cell you want them to become. And so they potentially can repair tissue that's damaged as you get older. So if you save your own stem cells from your placenta, you could potentially repair yourself later in life with your own cells. What's really cool is that scientists have been able to take cells that have already differentiated, we call them somatic cells, and been able to reprogram them into what we call pluripotent cells or stem cells. We've been basically able to manufacture, right, from adult cells that are already developed, manufacture clone stem cells, right, by doing a couple of steps, a couple of biochemical steps to basically make the cells go backwards in time to when they were stem cells. Right, so then it becomes, you won't even need placentas anymore to do this. If we can make pluripotent stem cells out of regular cells, you could fix yourself with your own cells. It's amazing. And then of course, combine all this with gene editing technology like CRISPR and restriction enzymes and all of that stuff. The potential for biomedical breakthroughs is huge using stem cells and pluripotent cells combined with genetic engineering. We should be able to fix every known disease that we have. That's cool. Isn't that cool? Wouldn't it be cool? You guys are the ones living through this right now. You're living through the age, this golden age of medical advances using genetic engineering, gene therapies, pluripotent stem cells, and a combination of those things make you able to design and change cells that have gone bad and otherwise healthy individuals, and you might be able to fix them using their own cells. That's cool. Anyway, I think it's cool. If I think it's cool, it's probably cool. Don't you think it's cool?